方法来解决这个 causality 的这样子的一个方法吧。然后其实简单来说 deeply information bottleneck 是关于对 variation autoencoder VAE 的一个延展。这个是我在那个答辩时候的这个 slide， 那我打算就是重新在这个讲一遍，作为一个也许之后会用得到吧。Okay, so let's get started. First, I would like to talk a little bit about the motivations. So there's a pretty famous sentence regarding causality, which is correlation does not imply causation. So what does this mean? Let's take a look at this very simple example. So we can observe there's a strong dependency between the ice cream consumption and the drowning rate. But we're not jumping to the conclusion to say that the ice cream selling forbidden can reduce the drowning rate. So in this case, we know there should be some hidden variables to influence these both events. In this case, apparently, it's the weather temperature. So during the summertime, the people, they are more likely to go buy ice creams and they're more likely to go swimming. And so in this case, the weather temperature, which is the hidden variables to influence these both events, which we call confounder or confounding variables. So that means there's a strong correlation between these two events, but actually there's no causal link in between. Okay, so the cause effect is existing in many fields in the world. Let's take a look at another examples. So the people in this case, people might assume that the darkness level in the child's room during the night might have something to do with whether the child has myopia. But the recent studies, they demonstrate, actually they show there's no causal link in between. And the real reason behind is that whether the child's parents, they have myopia. Because if they have, they're more likely to put the night light in the child's room, and they're more likely the child inherits the myopia from the parents. So it's pretty important for us to specify the distribution of the confounder. So in this case, if you know that the smoking is the confounders, then the people might not only try to stop drinking alcohol to prevent lung cancer, they might know that you also need to quit smoking as well. And okay, so estimating cause effect is also pretty important regarding the biomedical data sets. For example, developing the medications for patients, or maybe the doctors, they can offer the most effective treatments to the patients once they know what is the real confounders can influence both treatment and effect. Okay, so my project goal is to solve the statistical causality from a decision theoretic perspective, and I will talk about this afterwards. The causality. So talking about the confounding, first I need to introduce the concept regarding the regions. The regions, basically, that's just the data generating rules. So in this graph, we can see there's the intervention region, which denotes by FT, and the treatment, which is the cause, effect, which is the Y. And so there's two regions. The first is intervention regions. Basically, that just means you set the T, which is equals to 1, and all the effect that you have, which is according to all the patients who receive the active treatment. Like you can offer the painkillers to the patients, and either it can be set to 0, which means you collect all the effects based on all the patients who received the control treatment. Like you're not offering the painkillers to the patients, such as that. And but that's a little bit tricky, because in the real world we cannot like decide it's either offer the treated or untreated patients to the treatment to the patients, like this T is always fixed, which is no longer our choices. So this means that we only can have observational regions. That means all the available data have been observed. So in the real world, we can only calculate the cause effect based on the interventional regions. So there's so in this graph, actually there's no confounding case. So it is satisfied the conditional independence. Basically, simply say that's the effect you collect from the treatment group, which is not influence. It's not affected by the effect that you collect from the untreated group. Okay, so that is confounding. But as I said, this is no confounding, and this is not unrealistic in the real world. So basically, we should have something to influence the treatment and treatment effect at the same time, which is the confounder here. Also, we call it can be also called like the covariates or confounding variables. Yeah. And so, as I said, my project goes to solve the causal inference and the decision theoretic framework. So the DT framework, that is basically, it means that we only have two hypotheses. Either patients can be treated or untreated. That's why we only have our treatment group, which is said to be binary variables, either to 0 or to be 1. And so the causal inferences means we're measuring the differences between these two hypotheses. So in this case, the effect, the distribution of the effect is, we assume it is satisfy the normal distribution in the simple case. So which is okay. So with the causal inference, which is denoted by the average cause effect, basically just like calculates the expectations of the treatment group minus the untreated group. And as I mentioned, it's pretty important. We can only calculate these parts in the interventional regions. Either the patients can be treated or untreated. Yeah. Okay, next I'm going to introduce the model, generative model, and it consists of the pair of connected neural network, encoder and decoder. So the architecture of this pair of network can be like a multi-layer perceptron, CN or RN. It depends on what kind of data set that you have, and the encoder, which it has a high dimensional input, and which is learn a low dimensional and compact representation. We call this latent space. And the decoder, which is based on this latent space to regenerate something new, to generate new data points by minimizing the reconstruction errors. And so, as we can see, the generative model is kind of similar to a principal component analysis (PCA) in terms of the dimensionality reduction purpose. But as we know, the PCA is only try to find the largest k largest eigenvectors. So it only allows us to find the best linear reconstruction of the data, and that's the reason why we have this generative model. So let's take a very simple, the most simple case of the autoencoder. You only have 3 layers: input, latent space, and the output. So the encoder and decoder parts, it can be rewritten by the perceptron models, but basically they're just linear functions, like showing like this one. And and so the loss function for this case can be defined like this, and basically just minimize the errors between the input and output layers. So in this case, we use the least square method in this case, and this loss function, also you can call it objective function, can be rewritten like this part. So the purpose that I'm showing you these equations is just to demonstrate basically the the essential property of the generative model is just a combination of linear functions. But benefits from this kind of architecture, encoder and decoder, it has the ability to solve the nonlinear problems. And but as we know, the autoencoder has strong drawbacks, because it can usually the autoencoder is being used as for denoising task, but its lack of ability to regenerate something new and reasonable. The reason is that it only maps the high-dimensional inputs to fixed vectors, the latent space. So basically it's just a fixed variable, so it doesn't have ability to regenerate something new, because as we can see for these examples, MNIST data sets, we would like to make some variation for the original inputs. That's why we have these variational methods, which is called variational autoencoder, VAE for short. The only differences between the VAE and the autoencoder is that the variational autoencoder introduced this kind of sampling phase, and this kind of the prior will give it to this model, and which follows the normal distributions. And so basically the sampling we're sampling this latent space based on the parameters that we get from the posterior in the encoder. So you might ask, why we need this sampling phase? The reason behind is that it allows us to obtain a continuous representation. So that's why, because we have this continuous representation, and then we can decode something new and reasonable. So the objective function, I'm not going to show you how to derive it, but basically just minimize the negative evidence lower bound. So it consists of these two terms. The KL term, which denotes the encoder, and the decoder, which is just this log likelihood. But there's a drawback about these objective functions, because we know that for this KL term we can compute the partial derivative, and the gradient can be computed, but for this log likelihood term we can't compute the partial derivative. The reason is, if we just directly sampling from the parameters we got from the posterior, the latent space will become the random nodes. That's why we introduced this trick, which is called the reparameterization trick for back propagation. So the matrix comes from, we know that for each of the normal distribution, it's just an instance of the standard normal distribution. So for each normal distribution, we can rewrite it like this part. So instead of just sampling from these parameters of mu and sigma vectors, we're sampling from the standard normal distribution and combine it back to the parameter afterwards. Then by using this trick, we can obtain a deterministic node of the latent space. And so by this reparameterization, the back propagation, it can proceed for training. So now we already know what is the VAE model, and I'm going to introduce what is the information bottleneck. But basically, they are the same thing. The only the difference is that for the variational encoder, commonly they use as for the unsupervised learning. So you remember that we want to regenerate something new, and but for the information bottleneck, it is treated as the supervised learning. That means we have this labeling ground truth for the decoder part. Okay, so another difference is that the information bottleneck, which is on the basics of information learning, also combined with the deep learning. And the architecture of the information bottleneck is kind of the same. This also include the encoder and the decoder. The encoder actually just measure how much information in the input layer has been compressed into this lower dimensional latent space, and the decoder, which measures how much information regarding the ground truth it has been observed, so which is denoted by the mutual information here. And so the bottleneck, which is kind of perform as it keeps squeezing out the information in the resources and preserve the most critical parts inside in here for predicting the result. So on one hand, we would like to obtain the continuous representation of the latent space as compact as possible, but on the other hand, we want to preserve the information as much as possible as well. And therefore the finally we can obtain this continual representation, but it's just a multivariate Gaussian distribution. So in this graph, it's just two-dimensional case, so like two covariates here. And so for the objective function, we can rewrite like this, and the encoder part is also for the decoder part, denoted by mutual information, and the beta, which is the trade of parameters which control the balance between these two parts. Okay, so I'm not going to show you how to derive it, but that's the method we use for examining the variational bound, which is called a deep variational information bottleneck, but they are pretty the same thing. So we're not trying to target the exact distribution of the latent space. We introduce a variational distribution and use it to approximate the true one. And so it's you might feel this it's familiar because it's pretty the same thing with the VAE, and the only difference is that we replace this part, the ground truth, by the input data sets here, Y. So the Carroll term, Carroll divergence, which is also denotes the encoder, and basically it just like encourage the posterior towards the prior knowledge, because which is also satisfy the normal distribution, which we would like to encourage this posterior towards the prior knowledge that we give it to this model. And of course, the decoder part is also denoted by the log likelihood. Okay, so for now, we already know what is the cause effect, and we know what is the information bottleneck model, and finally we can combine these two together, and which is our cause effective information bottleneck, CIB for short. And the only difference is from our model to the information bottleneck is we are replacing the Y, the ground truth, to be a pair of treatments and the treatment effect pair. So as I mentioned, the ultimate goal for us is to find out what is the variables to influence these both variables simultaneously. So in our model, which happens to be the latent space, and there's another thing I need to mention is our model is only used to solve the measure confounding. That means that we only try to extract the most critical parts from the resources. So that means we're not trying to find something else, something hidden, which is not contained in the input dataset we have. So, and also, of course, the T, which is the binary variables and the intervention regions and the intervention variables. Yeah. So that's the way how I implement this model. And so for the encoder part, we can use the normal distribution to model the posterior, and for the prior, I set this to be 20 dimensionality here, and which we know that it follows the normal distribution. And for the decoder part, which is kind of tricky, because first we need to have this treatment model, and we use the Bernoulli distribution here. So you can imagine that we have two paths. We can switch in between treated or untreated, because we know for each of the data we have to label it, either it can be treated or untreated. And based on the treatment model, we can we can model the outcomes, and which is used the 5 layers here. This one is just 1 layer, and here we are use the normal distribution. So you can imagine we have 2 mean of the distributions, which is based on the treatment model, and therefore we can measure the how differences between these two means of distributions, and therefore we can calculate the causal effect. Yes, we can calculate the VAE. By calculating the differences between these two distributions. Basically that's how we model our data set here. And finally, by training this model, we can obtain the multivariate normal distribution, but it's in 20 dimensionality in our case. So for the experiment, we have the dataset which is called Infant Health and Development Program, HDP for short, and which is a real dataset, and usually they can be used for evaluating the causal inference, and this dataset is targeting the low birth weight and premature infants, and basically just study the impact of children's care services on this kind of premature infants, and the data which is collect from the mothers and also from the babies, and all the people, they are separated into 2 groups, and one group which is treated, which means that we offer the intensive children care and going to record the test from this group, and another control group, we're not offering this kind of children care service, but only just go to correct the test scores. Okay, so that is how the way that I'm feeding the data set into the network. And for each patient, so for each input, the inputs which is including the continuous and the binary inputs. The binary inputs, which can be like whether the gender of the babies, or maybe whether the mother is drinking alcohol during pregnancy, or the birth order of the child, and the continuous data, which can be like the birth weight, or maybe the newborn index, okay, something like that. So for each, so for the decoder, the ground truth part, we have the treatment and untreated, which is labeled by this binary variables. Either can be treated set to 1 and or 0, I mentioned it before. And for the ground truth of labeling Y, which is in this case is the cognitive score of the infant, so it's apparently they're just the continuous numbers. So for training, we stack the of the continuous and the binary data sets together for training. And first we need to plot our information curve, and the technology behind is that we gradually increase the number of the parameter of beta. So we start from a very small number, which is 1, to a very big number, and for each 200 epochs, we multiply the parameter of beta by 1 point or 1 gradually. So the purpose behind is that we would like to increase the parameters gradually. So this model, CIB model, the decoder part, tends to preserve more and more information. And of course, the encoder part, you will get, or say the latent space, where it will get less and less compact. So based on this and the CIB model and the data set we have, finally we can plot our information curve. So for each small green point, which is one CIB model with different beta value, And so for each green point also demonstrate the relationship between the compressed term, also the prediction term, which is denoted by the mutual information that I mentioned before. And this yellow line, just the mean line of the models with the star, which is the standard deviations. So this curve will construct gradually from the lower left corner to the upper right corner. And the ultimate goal we would like to plot this information curve is we would like to find when this curve is going to converge. So in this case, we'll find out the converge point, which is this red star point with the beta value around the 16,000. So you might ask why this converge point can give us the best performance. Because remember that I mentioned before, the ultimate goal of the information bottleneck is we want to find out the points when find out the points when the model with the minimum number of the compression term, but maximize the prediction at the same time. So in this case, it turned out to be the convergence point. So now as we know what is the number of the convergence points, and then we can plug back into our model and training the IHDB data sets for evaluating the average cause effect again. And so this is our performance with all the existing baselines. The first, which is the linear regression, the second, which is with a pair of linear regression, and the K-nearest neighborhoods network, okay, probably balancing linear regression, TARNet, which is kind of a feed-forward network, and the balancing neural network. And okay, these two I can't really remember what is that, but we are focused on comparing our results with the CVAE, which is cause effect variation autoencoder, but basically they are the same thing. The only difference is they only set beta value equals to 1. So it turns out our model has the best performance regarding the training datasets, also the testing datasets, because this number, which is calculates which is our prediction results minus the real ACE. That basically they are saying the average cause effect score, but basically they just the arrows. So small numbers which implying the better performances, and also this is just the mean with the standard deviations. So okay, so now this is our results. Now comes to the conclusion part. So the information curve is kind of like showing us the shortcuts for assessing all the model performances regarding all the values of beta. So it kind of we can pick the one with the best performances, because at this point the CEIB model owns the best generalization ability, because it has the minimum numbers of the compression term and also the maximum number of the prediction term. And another thing is, which is pretty important, because the CEIB model appears to be a sufficient statistic, because for most of the studies, like the variational autoencoder, for most of the case they just set the beta value equals to 1. So in that case, you can just cross your fingers to hope that the 1 gives you the best performance. But however, and for the information curve method, which is a sufficient statistic, so which is provides the guarantee for the performance reliability and the robust. Okay, so the future work I'm not going to show about this. I'm not going to say about this part. Okay, so thank you for your attention. So the thing is,那天其实我还准备了这个备用